In chapter 4 of our ECE 301 workbook, we're going to consider what are known as mesh currents, and specifically do mesh current analysis. This is another technique for resolving voltages and currents for circuits where, again, the resistances may not be in series or parallel. So this is sort of an alternative approach to node voltage analysis. So NVA is one approach that we've talked about using to resolve these voltages and currents anywhere we want in the circuit. So now we're going to look at mesh currents. But before we do that, we'd like to just sort of see how we could employ KVL in a way to resolve equations for voltages. Actually, equations for currents. Actually, we're going to use voltage equations to determine currents. We do the same thing with getting current equations, get voltages, vice versa, voltages for current equations for voltages, voltage equation for currents. So what you see in this very first diagram on the top of page 57 is these are circuits that we've seen before. Typically, we call these planar networks. So planar network means you don't have any crossovers. You can draw and flatten out the circuit completely on a plane, all right? No crossover, the wires don't cross over, the elements don't cross over, and so forth, okay? And so what we're gonna do is look at this simple circuit with these different branch currents. In other words, currents that are flowing through different resistances, all right? And we certainly could look at a KCL equation to describe this top node. But what we're gonna do is look at these separate currents in each branch of the network and resolve a system for finding them, for defining current 1, current 2, and current 3. In other words, I1, I2, and I3, using Kvl equations and all of the open areas of the network. So we'll start off by looking at a Kvl equation, let's say on the far left. And so I'll sort of indicate the path, voltage source A to resistance 1 through resistance 3. So that's just sort of indicating what the loop would be. And what I'm going to do is just simply apply Ohm's law there to represent all of the voltages that you would encounter as you went in the KVL loop, all right? And so we'll do this in a clockwise formation. So we'll just sort of mention over here that we're going to do this clockwise. And if we do that in this first loop, of course, we would encounter the negative polarity of that voltage source. So we'd have minus VA. But then representing the voltage through R1, the current is coming in. Let's just represent, for example, let's just say this is the positive polarity, negative polarity of that voltage, and it's PRC. So we'll just call this, we'll represent this as plus R1 times I1, again, because that would what the voltage would be. If we know what the current is, I1, and we know what the resistance is, then we know what that voltage is. And we're going to assume, because it's a resistance, right, that must have been the positive polarity, because we need to absorb energy. Similarly, if we keep coming around the loop, we would assume the same thing with the voltage being plus minus there, and we would have plus R3 times I3, and we would set that equal to 0, okay? So what we've done is, as opposed to KCL, we would have voltage terms here. Now we have the unknowns that we're trying to find are the currents, all right? And again, you would have to know what those resistances are, all right? So we can do another KVL loop. Again, this is to motivate mesh currents. We haven't done that just yet, so we're just motivating it. So this time we'll go over to the right side, and we're looking at going through, let's say, voltage source B or VB, and then we will continue on through R3 and then through R2. So we're doing that particular loop. And again, let's think about it being clockwise as we do that. So as we go clockwise there, now in this case, you can see that we would come up to the negative polarity. We're sort of opposing this polarity that we had here for the current coming here. So this case, we will say that would not be PRC, and we would represent the voltage as minus R3 times I3 in this case, because we're using we're using the current through that resistance, and we're going in the opposite direction of I3. So that makes sense. And then if we're coming up through the top there, then we're definitely coming from left to right through R2. And so the voltage must be, in that case, R2 times I2. This must have been the positive polarity, and that's the negative polarity. Again, it is a resistance. Now, again, once we've assigned the polarity here for this particular loop, we have to leave it the same way. We don't change it, okay? So we assign a polarity and leave it alone, all right? So you never flip reference polarities, okay? Just like you're never gonna flip the current's reference direction. It is what it is. We just have to make sure we're applying the laws appropriately, PRC or not PRC. And then as we continue on clockwise, we would hit that voltage source, V, and there we go, 0, okay? So we would have another KVL equation, perfectly good, involving 2 of the 3 currents. That would not be enough to solve. So we would need another relationship, and KCL would be ideal, right? Because we could do 8 KCL on the top node. And if we did KCL on the top node, we can look at what we're representing here in terms of the incoming currents and the outgoing currents. And you can see you've got I1 coming in, I2 leaving, and I3 leaving, right? So clearly we'd have to have the incoming has to be equal to the outgoing sum. And so we would have to have that relationship. Or maybe what we could do is solve for I3 and just say, well, all I3 is the difference between I1 and I2, okay? So the advantage of doing that now is then you could substitute I minus 1 minus I2 for I3, say, in both of the KVL equations. So in both KVL equations above, and in doing so, you would obtain a 2 by 2 linear system of equations for the unknowns I1 and I2. And of course, if you can determine what those are, then you know the difference between them is what I3 is, right? So what's very interesting here is this relationship here, that by looking at what we know has to be true KCL, there was this current flowing through. In this loop, we had I3 as a representation of the current flowing through the resistance. And over here, we see we have this current I2 coming through here because these two things are in series. And what's interesting is that what we have is sort of 2 representations of current coming through the same resistance, all right? And so that leads us to this concept of mesh currents. So I think you'll find mesh currents very handy. It's a very nice way of resolving independent equations, again, to be able to solve for unknowns. And what we're going to do right now is just see if we can define them and make sense of them, all right? So the central concept here is when you have several what we call mesh currents, in this illustration of the same circuit above, here's an illustration of 2 mesh currents. They're the currents that flow through these loops. So this we're going to call I1, and we're going to call this I2. Because if we look at these independently, all right, if we looked at that independent, clearly those elements are in series, and there's really one current flowing through them, right? But if we look at this loop, right, then again, you have another series of circuit elements, and there's one circuit flowing through both. But when you have both of them, you see, is one reason why we can't do that. That's why this was labeled I3, because we don't have these things. This is not an own series if you have this exit ramp here for that one, for example, right? So assuming a reference direction pointing downward, what we say is that when we have these 2 mesh currents represented through this mesh 1, this mesh 2, by definition, all right, the current through this shared resistance will be I1 minus I2. In other words, the current that we will say, if this is plus and minus in terms of the voltage, this is PRC, so we'll let this one be the positive one, and this will be the negative one. So in other words, if the mesh current, and typically we make our mesh currents, it's kind of a nice convention to make them sort of clockwise. They don't have to be, but it's a nice convention. If it's a clockwise mesh current, then this one is in making the resistance PRC, and this one is not, okay? So this one's sort of opposing. So the one that comes into the positive, we'll use that as positive, The one that's coming in the negative, we'll use that as a minus sign. And so the difference is I1 minus 2 as opposed to I2 minus I1, right? And so the voltage through the resistance is represented in this way as the resistance times that differential, okay? All right. The concept is that the current in the element is the sum of the mesh currents. And so one of them is I1, one of them is a negative I2, and so the sum is I1 minus I2, right? Very helpful for analyzing complicated currents. You typically draw them clockwise, as I said before, okay? And so we'll do a couple examples here. Go to page 58 and see if we can identify the appropriate mesh currents from clearly more complicated circuits. And that's the advantage of mesh current analysis, is you can handle now some more complicated circuits, right? So let's look at the situation we have here. Several different resistances, 2 different voltage sources here. And what I'd like to do is represent, say, the current and let's say the R2 resistance, okay? All right. And so in this case, what we're looking at is, well, what are the possible mesh currents that are involved? And in this case, you have I3 and I1, they're going through it, all right? This is the one that would be in PRC, so what we'll have is I3 minus I1 in that case, okay? Again, this mesh current, as it goes clockwise, would be flowing into the negative voltage polarity, okay? So it's important to keep in mind what your voltage polarities are, who's positive and who's negative, right? That would be R2. What about the current using these again, this is mesh current 1, mesh current 2, mesh current 3. The mesh currents are applicable to these closed loops, okay? So let's look at using the mesh currents, what would we say the current through R3 would be? That would be this resistance here. Well, there's I1 and I2 in play, right? Who's traveling in a way to make this PRC? It looks like I2, I1 is opposing, so it's I2 minus I1, okay? In this case, it's referenced upward. Again, because of what's going to make that absorb the energy, whereas over here, we're referencing to the left. We're flowing, you're thinking about the current flow, we're looking from right to left in terms of making that PRC, and the mesh current that's doing that for us is the one that's going to be positive, okay? A couple more examples. Let's do this more really complicated one. And again, all you have to do is find out for a particular resistance, what mesh currents go through it and who's positive and who's negative, okay? And most of the time, what we're seeing in these planar networks is just 2 mesh currents involved, okay? So let's reference R2, let's say upward, okay? In other words, we're looking at a representation of the current, let's say, moving up through this resistance like that, okay? And so if that's going to be our reference there, if we're saying that's what makes that PRC and makes that resistance absorb energy, looks like it would be in the direction of I4 and opposed by I1. So it would be positive I4 and negative I1 again, because another way to looking at it is if the reference of the current is upward, which one is in the same reference direction? I4 is. I1 is rotating in a way that it opposes that arrow, okay? So that's another way to help you know which one's positive and negative. Take a reference direction for the net current through the resistance. Which mesh current is in that direction will be the positive one, okay? Let's play again, R4, and let's reference the net current to the right, okay? Okay. So if we're going to the right, we're going this direction, okay? Then you've got 2 mesh currents represented with flows through that resistance. Looks like I2 is in the same direction and I1 opposes. So it'll be that will be the differential to get that current through it. What if we looked at the 8th one, R8 over there, sitting way over here at the bottom here, and let's reference it downward. again, the net current through it. In that case, we're looking at it from that direction. So again, what part and which meshes are involved, or who owns this resistance from the mesh standpoint, looks like the third one and the fourth one. Who is traveling in the same direction as this reference that we're taking? Looks like I3, and I4 is opposing, okay? Now, notice that if you were to reverse the net flow and say, well, what if we're referencing the current through R3 from an upward perspective, meaning instead of this arrow, we're doing this arrow, right? Then in this case, I4 would be in the reference direction and I3 would be opposing, and that would be how we do it. So that's how we use mesh currents, to define the net current through a resistance that is shared by different regions of the original network, okay? So we're gonna now use mesh currents to come up with Kvl equations and find linear systems to form from that. So at the bottom of page 58, we make a comment that if the network contains only resistances and independent voltage sources, you can apply this technique with mesh currents, with KVL. So it's very important. The voltage sources need to be independent, because clearly if the voltage sources are dependent on voltage or current elsewhere, we could get into trouble here, referencing the differential between any given resistance, right? Because they may not be, in this case, these currents are adjacent, right? They're connected directly, they're in the adjacent regions of the network, where if it's not a dependent voltage source, other parts of the network could be affecting the net current there. So, so just make sure we're looking at independent voltage sources when you're applying this technique for mesh currents. So we'll move on to page 59 and do an example. All right, and then we'll stop that, and then we'll pick up in the next lecture doing a couple of more examples. So let's do this example 11, which is at, again, top of page 59. Our goal is to create 3 independent voltage equations. So we will be using KVL with mesh currents, okay? And as indicated, we will take the initial end of each resistance encountered by a mesh current as the positive voltage reference. That is, always assume PRC as you travel around a given mesh, okay? So that's what we're going to do in this case, right? So we've already represented our clockwise representations of mesh currents. Again, always make sure the mesh currents are clockwise as our nice default there, right? And so, and again, we're assuming PRC as we flow through each loop, okay? So I guess I need to make a distinction here. Look at the polarities, all right, indicated for this voltage here. These, as indicated here, are the voltage polarities for the I3 mesh current. Why? Because in this representation, it's PRC, okay, right? So these are not the voltage polarities, not for I1, right? Because as this mesh current goes around, that would not be a PRC, all right? So again, we will always assume, and we will assume PRC as we travel around, okay, involving resistances, because they have, given their reference within a loop, they have to absorb energy, okay, all right? So, that's why I may have made some confusion arguments before, just to make sure that, you know, I said before, it's consistent for that mesh. You wouldn't want to change it within that mesh, but from the perspective of another mesh, yes, you could, right? For example, these polarities over here that are indicated for the voltage through R3 are clearly indicated for I2 to make that PRC, not for I1. If we wanted to represent the voltages for the perspective of I1, we need to flip those, okay? But as long as we're paying attention, you know, to the fact that we'll always be PRC, you're not going to get into trouble, okay? All right. So with mesh currents, we're always going to assume PRC. So let's do a KVL for mesh 1. Okay. And if we do a KVL for mesh 1, of course, again, we're just paying attention to the rotation clockwise through here. We would become through the negative polarity there, minus VA. I indicated before, we're going to assume PRC here. So if we assume PRC, then we're going to assume I1 comes into the positive pole of V2. And so we would get that voltage must be R2, in this case, I1 minus I3. See how I did that? Again, there won't be any flipping of signs here saying, oh, it's not PRC. No, it's always going to be assuming PRC within a mesh, okay? Within a mesh, right? The goal is just to say, well, which of the mesh currents will be achieving that PRC? I1 will, okay? Then we continue on through this resistance. If it's PRC, I1 is the positive one and I2 opposes. So we would get R3 times I1 minus I2, okay? And that would be equal to 0. So another way to think about it is when you're in mesh 1, that current index 1 is always going to be the positive one, the way we've done it, okay? If you go to KVL mesh 2, you can see the same behavior. Let's go to mesh 2. Mesh 2 is indicated over here by this mesh current I2. Again, we assume PRC as we go through, all right? So if we assume PR2, what we'll have for R3 is the net current will be what? I2 minus I1, because I2 will make that PRC and I1 won't, okay? Then we would come up through this voltage source. Its voltage polarity does matter. In this case, it's just plus VB. And then we're going to come down through R4. And again, if we're making this PRC, the voltage through this would be positive, negative, and we'll just get plus R4 times I2 and set that equal to 0. Okay. So hopefully that's clear in terms of who's positive and who's negative. In this case, I2 will always be the positive one for mesh 2. Okay. And then we'll do mesh 3. All we need to do in this case is those 3 closed paths will be sufficient to get voltage equations for current unknowns. In this case, it doesn't matter which direction we go. Let's start with flowing through this mesh current 3 is flowing through R2. Those voltage polarities are correct, right? And so what we would have is R2 would be multiplied by what? I3, and it's shared by I1, so we'll have minus I1, okay? And then if we come up through R1, there's only the mesh current itself, so it'll be R1 times I3, and then coming back through, we come into the negative polarity of VB, so we minus VB equals 0, okay? So there we have it. With mesh currents, we've now produced a system of equations so that we can solve for every one of those currents, okay? And if we have those currents, we'll get all the voltages that we need for all the circuit elements, okay? So let's just write the equations out and maybe do it in a way that we can see how to set up the matrix equation. First thing we'd want to do is find all, in the first equation, we want to find all the coefficients of I1. There's an I1 there, there's an I1 there, so it looks like it's R2 plus R3 times I1. And then what are the coefficients for I2? Well, I see a negative R3 there, right? So we could say that's going to be minus R3 I2. And then for R3, we have, for I3, what we have is a negative R2. So we'll have minus R2 times I3. And then that constant voltage comes over to the other side, okay? Just sort of seeing if we can see how all the coefficients line up next to these unknowns. Do the same thing for the second equation. The coefficients of I1 are just negative R3, so we'll have minus R3 times I1. Coefficients for R2, well, we can see that I2, we have an R3 and we have an R4, so we'll have plus quantity, I'll write it this way, R3 plus R4 times I2. And in terms of I3, there isn't any. There is no mesh current I3 in that, so we'll have plus 0. and we'll have the minus VB going over to the right-hand side. Let's see if you can do the last one. Yeah, look for the coefficient for I1. There's only one this time. It's going to be negative R2. What about I2? There is no mesh current 2 in that equation, so I got a 0. And then R3 should be a positive R3 and a positive R2, excuse me, R1 and R2 for the resistances. So we'll have R1 plus R2 times I3. And then the negative voltage sub B will come over to the right as positive. Okay? And there we have it. We have it ready to set up. Now we can set up our matrix equation with our unknowns as our mesh currents. And the right-hand side is 3 voltages, actually just 2 values, magnitudes. We just have a sign difference in those 2. So you can now read off what the elements of the coefficient matrix would be. The 1, 1 entry is R2 plus R3. The next entry in the 1, 2 position is minus R3, and the 1, 3 position is minus R2. Over here in the second row first column, we'll have minus R3, then we'll have R3 plus R4 on the diagonal, and then we won't have anything there. There'll be 0 there, with negative R2 here, 0 there, and then we'll have R1 plus R2 down here, okay? So you would have all these resistances, you would have the values of the voltages of the voltage sources, those would have to be given to you. Plug that into your matrix solver and out comes the mesh currents that we would have. And if you have the mesh currents here and the fact that we could represent the isolated cases of looking at, having the mesh currents, we know what the voltages are at every one of the resistances, okay? Right. So mesh currents are a very handy way, especially when the topology of the circuit is exceedingly complicated. Just keep in mind as you write these Kvl equations, think PRC every single time. Just make sure you choose the right differential for the currents through each resistance.